Hi, in this video, we're going to talk about interpreting the coefficients of a logistic regression model. All right, so if you remember back with regular old linear regression, what we said was on average, our target variable increased by the coefficients amount if the predictor variable increased by 1. Okay, that was on average. Now, when I'm doing simple linear regression, we have kind of a similar kind of a similar interpretation as logistic regression. With logistic regression, it gets a little bit more complicated because remember we have that S-shaped curve that we're using to convert numbers along the real number line to the probabilities between 0 and 1. And so because of that S-shaped curve, we can't take that straight forward, simple linear regression interpretation. We need to have a more complicated math in it. Now, it's not too complicated, but the interpretation is unusual to us who have never seen it before. And so we're going to walk into it just to see what it's like. All right, so our dependent variable is binary, 0 or 1, how we're going to represent it. And we're going to be mapping the real numbers into a probability is a major aspect of logistic regression. And so what we're going to do, we're going to say that the log odds is equal in the model is equal to the number along the real number line. All right, and that's how we're going to take our predictor variables with their coefficients and the intercept, which is anywhere along the number line potentially, and get converted over to a probability. All right, so let's go ahead and load our data. And so I'm going to use piping. I'm going to make sure that I don't get blasted in the face with digits. I'm avoiding scientific notation, clearing my workspace, loading my data for chronic heart disease. And then I'm just doing a little bit of data prep. I'm converting family history to a binary numeric column, a dummy variable, instead of having the raw values. All right, so now let's talk about interpreting a single continuous independent variable, it's the coefficients. All right, so first and foremost, we need to remember what is our fundamental formula when we're handling logistic regression. Now, I'm primarily going to focus on simple logistic regression because it's easier to handle. The extension to multiple logistic regression is pretty much the same thing. So I'm not going to spend a whole lot of time on it. All right, so here I have the log of the odds is equal to intercept plus coefficient times predictor variable. Okay, and so to interpret our coefficient, what I'm going to do is I'm going to consider what happens if I change x. And I'm going to consider changing it by delta x, so the change in x. All right, so now if I take this equation and I replace x with x plus delta x, then I get this equation. You can see that I've got, just a modified value of x here and here. All right, so now to interpret the coefficient, what I'm going to do, I'm going to subtract these two from each other. All right, so the left-hand side, I've got these two logs, and I'm going to do subtraction here. And then I'm going to take this and I'm going to subtract that on the right-hand side over here. Okay, so I have log of odds minus logs of a similar but different odds. And then I have these terms. So, all right, so the intercepts are going to cancel out. I see that I have a negative beta 1x. And when I distribute, I know that I'm going to have a positive beta 1x. So a lot of things are going to cancel out. So when I do this, the right-hand side is going to be beta 1 times delta x. All right, not too shabby. Now let's think about the left-hand side, logarithms. Well, I've got subtraction of logarithms, which converts to division. All right, easy peasy lemon squeezy. All right, so that means that I now have that the log of the ratio of the odds is equal to the coefficient times the change in x. Huh, okay. So now let's go ahead and simplify this. All right, so I'm going to take, e to the power of both sides, and that's going to give me the fraction on the left-hand side, and I'm going to multiply both sides by the denominator of the bigger fraction. So now I can see that if I have the odds and I change x by this amount, I'm going to be changing the odds multiplicatively by e to the power of beta times delta x. And that's going to give me my new odds. So now I have a direct relationship between the odds post-change with the odds pre-change. And it's going to be a multiplication by this amount. All right, so let's verify this. Let's actually go in and double check this. Okay. All right, so here, what I'm going to do is I'm going to calculate my odds here. So I went through, I built my model, and I'm going to just, for the predictions, I'm going to have obesity at 26 and 27. And so I want to see how are things going to change if obesity increases by 1, going from 26 to 27. All right, so here are my odds that I'm calculating. So I'm taking the predicted value here, and then I calculate the odds for each of them. And so the 26 is going to correspond to the original odds, and then the 27's odds that gets plugged into, when it gets plugged into here, is going to be the odds after the change in x. The x is going to increase by 1. Okay, so the left-hand side of the equation up here is just going to be that second part corresponding to the 27. I have 0.55. Okay, so now if I go and I apply the formula I had before, so I've got e to the power of the coefficient here, and so the delta x is equal to 1, so I didn't write it explicitly, times the odds of the first. Boom, I get exactly the same value. So that, that we can, this is a verification of the result. All right, so now let's think about what about if it was a dummy variable. So previously we looked at a continuous random variable. Now if it's a dummy variable, so how we represent categorical data, well, I've got a 0 or a 1. All right, well, that means that if I have a 0, delta x has to be plus 1. If I have a 1, delta x has to be a -1 because I'm going back to 0. Okay, so it's the same process, same game, same presentation, but now I just basically change x with d for dummy variable, and I have the exact same equation. Okay, so now the way to think about our dummy variables is that our dummy variable changes the intercept portion of the model. All right, well, what is that going to do? Well, if I go in and I actually manually plug things in, I'll be able to see that if I take the log odds when dummy variable is equal to 0, I'm going to get the intercept. And when the dummy variable is equal to 1, my log odds is equal to the intercept plus the coefficient of the dummy variable. Okay. And so now if I want to go through and just compute this, for the two possible cases of starting with 0, increasing to 1, or starting with 1 and decreasing to 0, I can see that I've got e to the beta 1 changing what's up. So what's happening here, this corresponds to taking the original intercept of beta 0, adding beta 1 in the log odds presentation of the equation. Here, this corresponds to starting with beta 0 plus beta 1 and then subtracting beta 1 to get the new log odds. So let's verify this. Let's double check that this is correct. And so here I'm going to use family history, which is the column that has the dummy variable in it. And so we've got 0 and 1 as our two levels of prediction. And so if I take the left-hand side of the equation, I can see that I get, get a 1. And now if I apply the formula that I have, and remember the formula has the change is equal to 1, so I don't need to actually do the multiplication in here. If I take the coefficient times the change exponential, then multiply by the odds, then boom, I get the same value I have here. Huh, isn't that interesting? All right, so now let's think about an interaction term. All right, so an interaction, how we can interpret an interaction is that when one predictor variable is fixed in the interaction, its coefficient changes with the value of the other one. So if a predictor variable is fixed and it has an interaction, then what we're saying is that its coefficient changes depending on the other predictor variable's value. All right, so let's go ahead and say that this is our model. So here's my log odds portion equal to the add-ins. All right, so now, well, let's go ahead and leave x1 fixed, but we're going to change x2. All right, so I'm just going to go in, just like in college algebra, and replace x2 with x2 plus delta x2. All right, and then what I'm going to do, I'm going to go through and do subtraction, just like I did before. And so I'm going to take this, and then I'm going to subtract the original log odds. That gives me this. I'm going to take this, and I'm going to subtract this. Okay, so now notice that intercepts are going to cancel. The beta 1 x1 is going to cancel. All right, this beta 2 x2 will cancel with this part when I distribute that beta 2. And here, this beta 3 interaction is going to cancel out with this part. All right, and so, a good amount of stuff cancels out. On the left-hand side, I'm subtracting logarithms, which is equivalent to dividing on the inside. And so I have the log of the ratio of odds here is equal to all of this. All right, so now I'm looking at this. I say I've got beta 2 and change of x2, beta 3, x1 change in x2 also. Let's go ahead and factor out the x2. And so now, let's go ahead and just keep simplifying it. And now here's that x2 floating around in there. So now remember previously when we looked at the continuous random variable aspect, I had a delta x2 in there, or sorry, I had a delta x, and that delta x was, we were interpreting what's going on with its coefficient. So what this shows us is that we're in the exact same situation we were in before, but the coefficient of x2 changes with the value of x1. Okay, so it's the same result, same interpretation, but we have to be mindful of the fact that when I have interaction, the coefficient of the variable changes depending on the other variable there. All right, now let's go ahead and verify this. All right, this time I'm going to check obesity and LDL. And so here I'm going to go ahead and do 4.3 and 5.3. Here I'm computing the odds like I did before. I'm getting the coefficients out of the model. Now the left-hand side is going to be 0.6. And if I do the equation I had before, notice I have the coefficients, intercept aspect. I have the coefficients for the interaction times the value of the other one. I'm multiplying there, and then I multiply by the overall odds. So here, this is my delta x2. This is the value of x1. And boom, I get exactly the same value. All right, so now let's do the same thing when instead we have a continuous random variable and a dummy random variable. All right, well, it's really the same game. We keep on playing the same game over and over and over. Hopefully, you're starting to see what's coming up. All right, and so if I just go through and rewrite what I did by just modify x's for d's in the right way, I'm going to get this equation here. So here, this is my my log odds when I'm changing x, but the dummy variable is staying the same. And here is the original odds ratio, and then I get this over here. All right, so I can go ahead and plug in values for D because there's only two. There's not that many to work out. And I can go through and just see exactly how it's going to work out. And you'll notice that here I just have the beta 2. Well, here when D is equal to 1, I have beta 2 plus beta 3. You can see that the slope changes depending on the value of the dummy variable. All right, so now we can go the other way with this, and it's the same game once again, that if I go through, I write this out, I'm going to see that the new odds is equal to the old odds times E to the same thing that we've got going on, but the slope of the dummy variable changes based off the value of X. All right, so let's go ahead and verify this. So I'm going to do the left-hand side of the equation I have above. With that, I get 0.33. And if I do the right-hand side of the equation computation, we see we get 0.33, huh? Now here we're going in the other direction. So that was based off of, using, so I think X was fixed and no, the dummy variable is fixed, and then the X variable was variable, and now here we're switching that around. And so, we can see that we get 0.98 and 0.98. So, it works regardless of how we approach this. Yeah, and I have other computations just to confirm this in other ways. Now we can also do the same thing for the interpretation of the interaction between dummy variables. And so here, the intercept is going to change depending on the value of the other dummy variable. And so, here we're going to end up having like very different intercepts depending on our 4 possible levels of our dummy variables. All right. All right, so for your homework, take your data, train a logistic regression model with a continuous independent variable and a binary independent variable and an interaction term, and just go through and do the exact same calculations I did, and just check to make sure that what you're seeing in the left-hand side of that equation is the same as the right. All right, that's all I've got for you. Life is short. Do math.